Good morning, everyone. I'm Young Koo, a lecturer at the University of Exeter, and my co-authors are Jose Capilla and Professor James Brown. Jose is at Arqiva, and James Brown is at the same university. I would like to talk about Moel-y. Yeah, okay.
The microphone doesn't.
It's not, yeah, okay, yeah. Right. Okay, I would like to talk about Moel-y-Parc HGM Mast, what is 700 MHz Clearance project, and the need for the tuned liquid damper, and the need for the structural monitoring. And here we had to develop time-synchronized measurement system using GPS and Arduino Mega 2560, and I would like to present the details of the SHM node development and the measured behavior and the conclusion. So Moel-y-Parc is at the north of Wales. Oh, sorry. Anyway, this is the Moel-y-Parc HGM Mast. It is 265 meter high, built 1962, quite long. The usually design life is 30 years, so that it is already over the designed service life. And it's servicing for digital television, digital and analog radio, and telecommunication clients. These are lists of mobile telecommunication companies. And it is owned by and operated by Arqiva, and their engineering consultant is Koei. And the green area indicates the high signal strength area for the digital TV. So the Moel-y-Parc is covering quite a large area. So 700 MHz clearance. Well, now there is a project to clear 700 MHz frequency range, which is being used for digital TV, but it is cleared because it needs to be used for 5G mobile broadband, because the increased need for the mobile broadband is taking over the digital broadband digital TV frequency range. So it is to be completed quarter 2 2020. And effectively, what will be affecting is many home need to retune the TV, and some homes need to replace their aerial, and some need to realign the area. For Moel-y-Parc, this means the old antenna and the new antenna for the digital TV at different frequency. These both antennae need to be at the Moel-y-Parc at the same time for about at least 2 years. So it means increased loading to the mast. The engineering consultant Koei assessed the Moel-y-Parc HGM mast for the additional loading, and their conclusion is the response is quite close to the limit, so that they recommended to increase the damping of the structure. And they came up with the tuned mast damper system. And it is designed for 4% at or higher, depending on the amplitude, bigger damping for the liquid tuned mast damper. And it's designed about this 0.575 Hertz and the generalized mass of 16 ton. Itself, tuned mast damper is about 1.2 ton. And it is installed quite top part of the mast. So this shows the bucket, which is used to carry the worker and the parts for the liquid tuned mast damper up to the top part of the mast. Without this, well, it is quite difficult to move all the parts and people from the ground to the top. Yeah. So the because we have tuned the liquid damper, and we need to make sure the tuned liquid damper is working properly, so that there was a need for a structural head monitoring system, and Arqiva required to measure such 5 nodes for the acceleration biaxial, and 1 anemometer at the top. Full-scale dynamics, which is a spin-off company at the University of Sheffield, where our group BES was at the University of Sheffield. So the Arqiva actually required us not to use the conventional approach of measuring system. The conventional approach means the sensor obviously is there, and that we can have long signal wires to the ground to a data acquisition unit. This approach is not acceptable because of the RF interference. Arqiva had previous experience that their signal cable is corrupted easily by the RF interference, because there are many antenna, and then they makes large radio frequency rich environment around the mast. So that means data acquisition need to be performed at each sensor node. That means distributed sensing system. But in this kind of distributed sensing system, we have another problem, which is time synchronization. Recently, I developed a time synchronization system using GPS module, and then that system was used in this SHM application. At the core, I used the GPS module, which is quite low cost, and it has 2 outputs. One is NMA sentences. NMA is the standard format, output format for GPS devices, and it starts with some keywords, and it follows the data. For example, this is time, latitude, longitude, and this is the date. The second important output from the GPS module is PPS signal. PPS is a scale wave coming out of the module at the exact start of each second. So at this moment is the exact start of this second, and next second, and the second following. In the previous systems, well, there was time measurement, time synchronization system by using NMA sentences. But the problem is, NMA sentences comes out from the port roughly in the middle of 2 adjacent PPS signals. But the timing varies depending on the workload on the module. So that if we use these NMA sentences to capture the time, the accuracy is quite limited. But when we know the time by passing these sentences, and then when we have a next PPS signal, we know the exact time by adding 1 second from this time. So by combining these 2 outputs, we can achieve very accurate time information. The accuracy is up to 1 microsecond, better than 1 microsecond. The module can be wired into a Raspberry Mega, and Raspberry Mega process has a crystal oscillator, which oscillates 16 mega times per second. So at each oscillation of the crystal oscillator, 1 instruction is performed on the microprocessor unit. And the microprocessor unit has a very special device, which is a clock counter. So every time clock oscillates and then the processor executes a instruction, the clock counter increases. So by passing these 2 information on Arduino, we can identify exact time of the PPS at time k and time k plus L. I assume the time difference is L, second. When we have PPS coming to the Arduino, we can record the clock count here, And then next PPS, we can store the clock count as well. Every time we make a measurement between the two, we just need to read the clock count. And then what we can know is, because we know the exact time at this point and this point, we know the time difference here, which is L. And we know this point, so we know the difference between the clock counts. By using the similarity of two triangles, so we can identify the length between this. So that by adding this length to this time, we can identify the exact time for the measurement made. And this is explained in this paper. Actually, the system is for time stamping, not time synchronization, but time synchronization can be done by resampling. Each node can start at different times, so that we have no guarantee about their starting time. So they start, arbitrarily, and then their clock crystal oscillator may have variance depending on the temperature. So they can be well like this. But by performing resampling, we can synchronize all the measurement at the same time. And you can look at this paper for the detail. So before we use this kind of idea for the Moel-y-Parc high-guide mast, we needed to make sure 2 points. The first one is our equipment can survive the RF-rich environment, and second one is the GPS module can receive the GPS signal for the time stamping accurately. So we had a prototype system, and this is Jose, my co-author. And to move this box up to the mast, well, the climber needs to have a license to climb and full equipment. And then their colleague has brought the box to the top. So here, this is me, and there is some orange part of the colleague, yeah. So now, the system overview is this. So we have 6 nodes, and the 110 volt main power has been provided, and the network between the node is by the fiber optic cable. At the base, there is a base station, and it has a 3G, 4G router to upload the measurement file to the FTP server at the University of Exeter. The sensor I used was Colibris BS1002A, which is quite a reasonable sensor with low cost with high performance. And I used ultrasonic anemometer. And this is the acceleration node. We have 5 boxes of acceleration node, and this is media converter for the fiber optic cable. And this is the node I developed with a display at the top. And this is the sensor, and the others are power-related parts. For the acceleration node, it has Raspberry Pi at the bottom, which works for the time stamping by Python code and for wired data transmission to the base station. And at the top of the Raspberry Pi, there is a GOM node, which stands for GPS plus OXO plus Arduino Mega for accurate time stamping. OXO is useful because it can keep the exact time even though there is no GPS signal at all. And there is another 24 bits 4-channel simultaneous ADC board and the display at the top. This is the GOM node for the time synchronization, and this is the sensor board, and this is the ADC board developed. This is the anemometer box, and this is the base station. So all these are media converters and switch, and Raspberry Pi and external hard disk. These are measured behavior, so RMS and wind data. Well, we have a large gap, which is quite nearly unavoidable in SHM applications. And this shows the OMA result. We can see this is a week data, and we can see the OMA the natural frequencies are quite dirty, so there is kind of a challenge involved to identify or to track the frequency accurately. And the future work is actually BAYOMA, which gives us the estimated natural frequency and damping and their confidence interval, which is quite important because damping estimation is quite uncertain, and BAYOMA can give us the impedance interval. In other words, we can change some parameters, time length of the record or the noise level of the sensor. By changing the sensor, then we can control the final confidence interval or one standard deviation level. So yeah, thank you very much.